Pin myself here. I like your picture, Jessica. I like your video. I don't see you anymore because you're on video, which is fine. Thank you for being on video. Let me pin myself. Pin. Cool. Oh, I guess I can see over here. Can I? No. Anyway, not a big deal. Welcome to class. We're getting started here. Couple things, the usual things. So just reminder, where are you? Link that I want. Where's the chat? There's the chat. Here is a link to the attendance sheet. We'll do this every class. Go fill it out when you have a moment, preferably as soon as possible before the end of class. What else? There were a couple things I just wanted to remind you guys about. One thing, two things. First thing, the 10-day drop deadline is tomorrow. Not that I don't know if this is a 10-day drop class, but just for your classes in general, I thought if you get to remind everybody that tomorrow is the 10-day drop deadline. So there was a class you were taking that had a 10-day drop deadline and you're thinking you might want to drop it. Tomorrow is the deadline to do so. The other thing I wanted to mention was I did grade all your quizzes. They were pretty easy to grade because it was pretty short. I tend to make the next quiz a little more, I left my water in the other room, I'll get it in a minute. A little more, what's the word I'm looking for? I don't know. A little more thought-provoking, not just straight up calculation, but this class is a little more challenging to come up with good questions. So there's that. And I did provide comments on your quiz. So if you go look at your graded quiz in Canvas, everyone will see that they've gotten full credit on all the problems. But if you go look at the comments or the things I've selected, that should give you some information. But you actually will have to go look to see what you did, because if you just kind of glance at it, like, oh, I got full credit. Well, everybody got full credit. So if you want the feedback, you need to go actually look at the quiz in Gradescope to see kind of what's going on there. So again, for those of you just joining, here's the attendance doc. Go click on that and fill it out. Oh yeah, it's annoying. Can I make that a link? Nice if that was just clickable, but I don't think I can. No, okay. Oh well. There was one other thing. Nope, I guess not. So I've been looking at what both of your teachers are doing, and it seems like they're kind of starting to diverge a little bit from each other. You know, as is typical, especially when people are using different books, not all the content's going to be the same at the same moment. So I'm going to start off every class by just asking, do you guys have any questions? And they can be very specific questions like, hey, can you do this example? Or they can be very general questions. And I do have Nimdari's kind of handouts up to look at if you have questions about his handouts. I also have Whitener's material available to look at if you have questions about that. So I'll go grab my water while I give you a minute to think about if you have any questions. Oh, that's loud. The skewness of a box plot. That's a good question. So sure. Yeah. So actually, I mean, I think I can. I don't know the answer off the top of my head. Getting all this black dust over here. So let's look at some data. I feel like I had some good data the other day. Yeah. So I will remind you guys, the hard part about this class is going to be coming up with examples because it's hard to just create data. So let me refer to the, well, actually, so let's just look at the picture first of all. So if this is a box plot, let's say we have, so here's what all these things mean. So if there's no outliers over here, An outlier is something that's defined to be further than 1.5 times the interquartile range away from one of the quartiles. And I'll say a little bit more about that in a minute. So here's what all these points are. This middle one here is the median, which is also known as Q2. It's the second quartile. It separates half the observations, half are above this value, half are below this value. This is the first quartile. 1/4 of the observations are below it, 1/4 of the observations, sorry, 3/4 are above it. This value here is the third quartile. I think we actually don't use a subscript, it's more written just right next to it. And again, for the third quartile, 3/4 of the observations are below it, 3/4 are above it. You could also call this the 25th percentile, the 50th percentile, and the 75th percentile, because 75% of the data is below it, 50% of the data is below it, 25% of the data or observations are below it. This value here, if there aren't any outliers, this is the minimum here. If there are outliers, the outlier is the largest value or the smallest value. This value right there is the biggest value within Q3 plus the interquartile range. And the interquartile range is 1.5 times the difference between the inner quartiles, Q3 and Q1. So if all your values are within this, you don't have any outliers, but if you have an outlier, then this is kind of the next biggest value that's still in the inner quartile range. So here's what I'm looking at when I see this. I see that the median's right here, and so there's a lot more data right here, right? So there's a lot more data in this small part here, where here the data is kind of stretched out, right? We've got more kind of variation in this quartile. Yeah, definitely seeing your questions there. Good questions. I will get to those. Now I'm actually having to think a little bit about like, okay, so what does it mean? Does it mean so actually let me back up just slightly. When I think about skewness, I really think about, so if the data looks like that, where it's kind of, you've got this large tail to the right. So again, when I think of something like this, I'm thinking of like household incomes, because there's a really small number of household incomes. It's kind of my go-to example. I'm not gonna lie, it's one I use a lot in my brain. Things way out, there's a few people way out here that are making lots and lots of money, and there's most of the people in here. And so this is where an example when it's skewed to the right like this, where the mean is greater than the median. Or as I think of it, the being skewed right pulls the mean to be larger than the median. Whereas if this isn't skewed right. On the other hand, down here, if you have the opposite kind of situation where you've got a tail to the left, kind of data like that, here the mean is going to be less than the median, because there's a whole lot of, or there's some really, really outlying small values that are going to drag down your average. So this is skew left. So I guess the question here that I'm trying to answer, and I'm really like, I don't know the answer, I'm really trying to think it out, is if this was my box plot, how could I tell where the mean was, or what would be a good guess as to where the mean was? And I see, well, here's what I see. I see more values that are, so in here, so in this section, there's 25% of the values. And in this section, there's 25% of the values, approximately. It's not always exactly 25%, but close enough. Oh, I know what I wanted to say was the other thing. I did make a video about percentiles. We can still talk about percentiles for sure today, but there is a video on YouTube if you want to look at it with some percentile examples. So that's there for you guys. It's linked in Canvas, and yeah. So here's what I'm thinking. This is not exactly precise, but it is, I think, the right thought process. These values are more stretched out, meaning this value over here, like if there's something over here, an observation, compared to this observation here, this is going to pull my mean further up than this will drag it down. So since there's more space in this quartile that's above the median, I feel like that's pulling the average up above the median because there's values here that are further away from the middle value. So if I had to guess, I would guess that the mean of this data is greater than the median because there's more values that are further away from the middle value here, which when the mean is greater than the median, to me that seems like it's going to be skewed right. Again, I will fully admit this is just kind of my thought process here. There might be questions in the book that actually address this. Let me take a look real quick. Let's see. No, I'm right in the right spot. Sorry, one sec. Yes. Okay, so here's what I found it. So I'm looking at the text, probably not the right edition of the text, but I'm looking at the text from the Midari's class. I'm kind of section 2.8-ish, or right before 2.8. For interpreting box plots, it says here, if you visually compare the length of the whiskers, if one is clearly longer, the distribution of the data is probably skewed in the direction of the longer whisker. So I was kind of doing that, except I wasn't looking at the whiskers. I was looking at I'm not sure what these parts are called. These are the whiskers. Well, actually, I better double check that because the whiskers, let's see. Change. Whiskers. Yeah, good, okay. Yeah, these lines here are called the hinges. These are called the whiskers. So if one side has a noticeably longer whisker, it's probably skewed in that direction. So here, the whisker, although I drew them kind of the same length, there's also this outlier way over here. So I would definitely say this is skewed to the right. Again, there aren't any numbers here, so it's kind of just making stuff up. But that's what I would say is that if whichever side has a noticeably longer whisker, your data is probably skewed that way. And again, because if you've got values that are further away from the middle, they're going to pull the average up if they're higher, or they're going to pull the average down if they're lower. And pulling the average up above the median means we're skewed to the right. Pulling the average down below the median means we're skewed to the left. So that's my kind of thought process there. I'm liking your guys' pictures, by the way. Thank you. I appreciate seeing images as opposed to just names. So let me look at the chat here because I know you guys have been asking some other questions. Also, once again, here is a link to the Google Doc for your attendance. Please, everybody go fill that out. Let's take a look here. Sorry. I know there's my face. Okay. Can you explain what the percentages mean when calculating standard deviation? The percentages. I'm not sure what that question means exactly. I'm going to think about that as well as the z-score in relation to the standard. Okay. So to answer Mercedes' question there, yeah, mean is greater than mean, it's skewed right. Like the percentages in the graph. Cool. Okay, so all the rest of the questions seem like they're about kind of z-scores and standard deviations. Great. And so there's definitely, I definitely did talk about this in the video I made that I posted on YouTube, but that doesn't mean we can't talk about other examples. So I'm going to make some stuff up because I am. So let's say for the population, I actually had a real example, but I like shoe size. Shoe size is easy. So let's say for the population of men, why men? Because I'm a man. let's say the average shoe size, and again, I don't know if this is true, I'm making up numbers, it's fine. Average shoe size, let's say it's 10. And the standard deviation, let's say it's 2. And so we're pretending that these are the actual population numbers, meaning for all the men in whatever population, either, definitely Francesca. We see maybe this is all the men in the United States, maybe this is all the men in the world, whatever our population is, these are the statistics for our population. So I'm going to kind of go with the 68 stuff first, and then we'll kind of get further in depth here, because I don't know how much you guys are really doing yet. So there's kind of, I think, 2 ways of asking questions about this. I could either ask questions like, for some shoe size, like for a man who wears size 12, what percentage of the population is their shoe size bigger than? Okay, and then the other type of question we can ask is, I'm going to make this easy. What shoe size let's make it, I'm going to ask the easy ones at first. Do 2.5% of men, the phrasing here is challenging. What shoe size, I want to say what shoe size do 2.5% of men have bigger feet than, which sounds dumb. What shoe size do 2.5% of men have a larger size? And the phrasing here is terrible, I'm sorry. Basically, what's the lowest shoe size for the top 2.5% of men? Okay, top meaning the biggest, whatever. So basically the question is, I give you the shoe size, what percentage of people have a shoe size that's smaller or bigger than that? Or if I give you the percentage of people that have a smaller or bigger shoe size, what is the shoe size? So let's answer the first one. And let's go to the other side. So the normal, pun intended, the normal assumption here, you're like, what pun? Well, you'll hear in a second. The normal assumption here is that the population is distributed normally. There's the pun. Yes, I will make all the terrible puns in this class. So the normal assumption, the usual assumption for data is that it's distributed normally, or in a Gaussian curve or a bell curve. So we're looking at a distribution like this, which should be symmetric. I didn't draw it exactly symmetric. And the mean is exactly whatever the mean is, which we said is 10. And the standard deviation is what we said was 2. And for a normal distribution like this, we have the empirical rule, which is the 68, 95, 97, 99.7 stuff, which says that you have 68% of the data between one standard deviation on the other side. So what that says in this particular example is 68% of men wear between a size 10 and 14. Right, one standard deviation to, oh, sorry, that's wrong. The mean isn't 12, the mean is 10. That'd be between size 8 and size 12. Once again, for those of you that just entered, there is the attendance. 95% of men wear between 2 standard deviations in either direction of the mean. So that would be 10 minus 2 times 2, which is 6, and 10 plus 2 times 2, which is 14. And 99.7% of men are included within 3 standard deviations on either side of the mean. So 99.7% of men wear between a size 4 and 60. I feel like a size 4 is pretty small, but I suppose it's possible. My brother definitely wears a size 17 shoe. He's got gigantic feet. So this seems maybe reasonable. Again, it doesn't really matter for this example if the data is right. I get a little lost in this part. Can you explain where you get these numbers from? Totally. So here's where these numbers are actually coming from. They're coming from what's called a Z table. So the very, very long mathematical answer is that this is actually, you could graph this function. There is a function that this is. It's not super, I mean, it's not terrible. This function is f of x equal to, oh gosh, what is it? It's e to the, I don't remember exactly. It's something like e to the x minus mu over sigma squared over like the square root of 2 pi. It's something like that. You do not need to know that. But the idea here is that the way you could find, so in this example, the function would be something like, and I'm sure I'm missing some little piece here, so don't quote me on this, it's not exactly right. But this function here is something like e to the x minus 10 over 2 squared. I think there's a negative sign out here, actually, over the square root of 2 pi. And I'm sure there's probably another sigma among. But you could find, so if I was trying to find how much data was between sizes like 8 and 12, which we know is 68%, the really, really long answer, the way you could find that is you could actually do an integral. You could say, I'm going to do the integral from 8 to 12 of this function. We're not going to do that. In fact, this function actually is not integrable. You can't find the antiderivative of this. Yes, in the normal distribution, we are assuming the mean and the median are the same because of the symmetry. Right? There's no skewness to the right or the left, so the mean and the median definitely get to be the same. So the long way to answer this is you would do the integral to find the area under this curve. And the area under the curve between 8 and 12 would be exactly 0.68 or 16%. The shorter but still kind of longish way to answer this question is, instead of doing that, we would look at the Z table. And so I'm going to pull up a Z table. I think I had one up, but I might have closed it. So let me look real quick here, and I'll show you guys. There's definitely, there should be one in your book, but you can also just do a Google search. And yeah, so let me share my screen with you guys for 1 second. More than 1 second, maybe. Yeah, come on. Share. Okay. So looking here, here is a Z table. We'll have to talk about the Z score. But the Z table says, so actually, let me back up. I'm going to stop sharing for a second, and then we'll come back to this. So before I can talk about the Z table, I should probably talk about the Z score, which I know we talked about last time. So the Z score is just the number of standard deviations that a particular score is from the mean. So without having to do any math, really, I can see that a shoe size of 12 is 1 standard deviation away from the mean. So is a shoe size of 8. So the way we differentiate between those is a shoe size of 12 is a positive 1 Z-score, and a shoe size of 8 is a negative 1 Z-score because it's below the mean. A shoe size of 14 would be 2 standard deviations away. So the Z-score here would be 2. The Z-score for a shoe size of 6 would be negative 2. Now the way you actually calculate the Z-score, it's given by whatever score you got. So your observation or your score or your value minus the mean divided by the standard deviation. This top part of the numerator of the fraction tells us the difference between our score and the mean, right? So like 12 minus 10, that's a difference of 2 shoe sizes. but then we have to divide by the standard deviation to say how many standard deviations that is. Totally, yeah, we can, yes. Yeah, I know exactly what your question is, Mercedes, and we'll definitely get to that. So in this case, like for a score, for a z-score, so for like a size 12, we see that the z-score is exactly 1 because it's just 12 minus 10 over 2, which is 1. So for the numbers that are nice, meaning they're exactly 1 standard deviation above or below, or 2 above or below, or 3 above or below, the math is super easy. And you can usually just kind of, at least for easy numbers like this, you can tell, oh, that's what it is. Now, the question I want to answer here is, and actually, let me put this here. Yeah. So the question, Mercedes' question is great. So one of the questions in her homework said to find what proportion of this data set is 84% above the mean. Not exact. So the question I think is trying to be asked there is, what shoe size is 84%, is above 84% of all the other shoe sizes? So what's the actual number or actual value, shoe size is my example, that is a shoe size that is bigger than 84% of the population. And you're right, that 84% is not one of those 3 numbers, 68, 95, or 99.7. So there's 2 ways you could do this. I know the way they intend you to do this, well, they intend you to still use this rule. But I will just point out, because I think it's worth, you're definitely going to do this eventually, so you might as well mention it right now. If I was going to do this, and let me share my screen with you now for real. Sure, yep, share that screen. Okay. So I'll do this. Go away, sorry. So one way, if you look at this Z table here, this, and there's different versions of the Z table. And I can even make this bigger if you guys want. This Z table says for whatever your Z score is, the number that's in the table is the amount of area in the shaded part. So the amount of area that's in the less than that number value. So if I look at a Z score of, well, if you look back here, for size 12, my Z score was 1. So if I look in my table at a Z score of exactly 1, so where did I find 1? It's 1.00. Oops, I don't want to do that. So there's the value right there of 0.8413. What that means is that for a Z score of 1, that value, the shoe size, which was size 12, is greater than 84.13%. Well, let's just round it out to 84% of the data. And that's one way you could do this. Now, I don't think that's what they actually want you to do, but I just want you to see that that is an option in general. Let's stop sharing. Now, here's what they really kind of want you to do using this empirical rule. So, yeah, let's do this. So I know that within 1 standard deviation of my mean, which again is the sizes 8 and 12, that's 68% of the data. How much is left? Well, 32%. So there's, and the nice thing here is we do have symmetry, meaning that it's always going to be the same on either tail end here. So that 32% that's left over is split up as 16% over here and 16% over here. So 16% plus 68%, that's 84%. And so I can say a size shoe 12 is going to be bigger than 84% of the data. I could also say a size H, I think I said a size shoe 12 a size 8 shoe is going to be less than 84% of the population. It's going to be a smaller shoe size than 84% of the population. I could ask a similar question. So how much of the population, so if I wear a size, let's say I wear a size 14, what percent of the population am I wearing a bigger shoe than? Sorry if my writing is not super nice. Okay, well, if I'm wearing a size 14 shoe, that means I'm up here 2 standard deviations away from the mean. And I know that within, so I'm going to erase some of this here. I know that within 2 standard deviations, there's 95% of the data. So that means how much is left in the ends?
2.5%.
Great, exactly, right? 2.5% in each end. So you can either add this and this to say that my shoe size is bigger than 97.5% of the population, or you can look at the percent I'm not bigger than and subtract that from 100%. 100% minus 2.5% is also 97.5%. So if I wear a size 14, my shoe size is bigger than 97.5% of the entire population. Okay, we can make this even more interesting. We'll go back to the other side here. I'm going to try and make it a little bit nicer. Okay, this picture's way better. Yeah. So here's a harder question. What percent of the population wears between a size 6 and an 8? Okay. Well, here's what I'm going to say. I'm going to say I know between 8 and 12, that's 68%. Right? And you could actually kind of go, there's actually 2 good ways you could do this. I'm going to do it, I'll show you both ways. And then I know between here and here is 95%. So the green section here and here should be the difference between 95% and 68%. So the green section is 95% minus 68%, which is what? Not quite 30, it's 27%. But then I don't want both green sections, I really just want one of the green sections. Well, again, symmetry means everything on this side is exactly the same as everything on this side. So this area here is the same as this area here. And since they add up to 27%, they each have to be exactly half of that. So between 6 and 8, between size 6 and size 8 is going to be half of 27%, which is 13.5%. Another alternate way you could have done that is just doing it in terms of being half at first. You could have said, so alternatively, if I'm just thinking of the left half of things, here's 10, here's 8, here's 6, here's 4. I know that within one standard deviation on either side is 68%. So one standard deviation on just one side is going to be 34% of the data, right? Half of 68%. And then I know that within 2 standard deviations, I mean half of the 95%, which is 47.5%. And then within 3 standard deviations, I'm going to get half of 99.7. The half of 99.7, I know that 99.7, I'm 0.3% away from 100%. So if I do half of 0.3 away from 50, it's going to be 0.15. So I'm going to be at 49.85% of the data is within 3 standard deviations of just one side. Right? Because if you double that, you should get 99.7. Okay, so if I want to find what's in here, it's just the difference between 47.5 and 34. And 47.5, that's a squeaky pen, minus 34% is going to be exactly 13.5%. So either way would work to do that.
So essentially, we're just taking the numbers that we do know and working backwards from that.
Yeah, exactly.
Okay, that makes sense. Thank you.
Yeah. You could ask other questions. So you could ask the question like, what shoe size is smaller than, I don't have a good question. Sure. What shoe size is smaller than 16% of the population? So if I said something like that. Just to clarify though, no one's actually using the Z table yet, right? It's all just based on these empirical things. Is that true? Or I should ask, is anyone using a Z table yet? If you don't want to say words, you can click on the little yes or no thing in the participants. I could actually see what you guys are saying. Can I? Yeah, I can. Okay, I see some no's. All right, I see that. No. Okay, good. Yeah, so no, good. All right. You definitely will eventually. Z tables are great. But to answer the question I just asked, what shoe size is a shoe size that's smaller than 16% of the population? So I'm looking for the size over here where I've got 16% over there. Well, that means there's 84% over here, which means there is, sorry, this is 84%. So this section right here is 84% minus 50%, which is 34%. Oh, but that looks like the number that goes with one standard deviation, right? We definitely know that if this is our mean plus one standard deviation. So if this is 10, that's 10 plus 1 times 2, which would be a size 12. So a size 12 is smaller than 16% of the population. It's also bigger than 84% of the population. Okay, so let's see, what else have people written here, just to see if there's anything else I'm kind of missing about this. All right, so are there more questions about this? Again, there is another briefer example similar to this on YouTube using IQ scores with the normal kind of mean of 100 and standard deviation of 15. That's a fairly typical example. What else? The board's getting real. Time to clean the board area. I got a lot of this black dust, which is terrible. Right. So I was definitely looking at some of the upcoming material. Where'd you go here? And I saw that, at least in handout 2 for Nimdari's class, you're starting to look at probability rules. He's got some examples there. And so a couple things to be aware of with these probability rules. So there's some notation that can take some getting used to. Typically, so in fact, going back to the example we were just using, one way you might write some of the things we were saying is, for our population with shoe size, again, with the mean being 10 and the standard deviation being 2, a way I could have phrased that last question would have been, what's the probability that my statistic X is greater than a size 12, right? What's the, actually, that's not quite the way I phrased the question, sorry. But that's what I'm gonna say this time. what's the probability, or what percentage of the population has a shoe size that is greater than 12? Well, the probability that X is greater than 12 is the same as the probability that Z is greater than 1. Where am I getting that from? Well, I'm just changing X to a Z-score and 12 to the corresponding Z-score. So this becomes X minus 10 over 2. That's my Z. And this becomes the same thing. 12 minus 12 over 2. That's not right. Not 12 minus 12. 12 minus 10. Which is equal to 1. So again, when I'm asking what's the probability that X is bigger than 12, I'm really just asking what's the probability that I'm bigger than 1 standard deviation above the mean. And again, that's where I just look at, okay, that's going to be, I'm over here at 1 standard deviation above. I know that 34% of the data is right there. I know that 84% of the data is there. I know that 16% of the data is there. When you talk about probabilities, typically your answers aren't written in percentages, they're written in decimals. So I would say that the probability that X is greater than 12, where X is the shoe size, the probability that someone's shoe size is greater than 12 is 0.16, or you could say 16%. Either way would be fine. And this is fairly typical notation for a probability of something happening. And it really kind of depends on your data. So I'm looking at this example from Mindari's class. And again, there are other things you want to see, just let me know. But he's got some data of, so I'm looking at the very first thing. Suppose the frequency of age among unemployed residents of a city is as follows. And here are the ages. So the age, then we've got age groups. So we've got 15 to 25. We've got 26 to 35. We've got 30, well, obviously 36 to 45, 46 to 55, and 56 to 65. Those are the ages we're looking at. I just want to point out, if your data is written like this, I think, and I know Whitener was saying something about this the other day in class, this probably really means your ages are like 14 and a half to 25 and a half, and 25 and a half to 35 and a half, right? So the in-between people get grouped into one bracket or the other. And then we have the count, or the frequency, and the numbers are 2,500, 1,500, 500, 1,000, 1,500. And then you could also talk about the relative frequency. And the relative frequency is just the number of people in a particular group divided by the total number of people. So, right, if I say like 2,500 people between the age of 15 and 25 are unemployed, it doesn't have a whole lot of meaning without more context, right? You're like, well, out of how many? Out of 1,000? Or that doesn't make sense. Out of 10,000 or out of 10 million, right? It's kind of, we need to know what the larger population is to kind of make sense of what the data actually means. So here, the total of this is 2,500 plus 1,500 is 4,000, 4,500, 5,500, 6,500, 7,000 is the total number of unemployed. So the relative frequency of people age 15 to 25 that are unemployed is 2,500 over 7,000, which reduces to easily 25 over 70, or if you want to factor out another 5 out of 14. And then you need a decimal or a calculator. Here, 1,500 out of 7, this is going to be 15 out of 70, or again, 3 out of 14. This is going to be 5 out of 70, or 1 out of 14. This is going to be 10 over 70. That's too easy to reduce. That's 1 over 7. this is 15 over 70, which is going to be 314. And all these relative frequencies should add up to 100% or 1, right? If you add 5 14ths plus 3 14ths plus 1 14th plus 1 7th plus 3 14ths, it definitely adds up to 14 14ths, which is 1 or 100%. So then we can ask questions like, so, and here's where we have to kind of be explicit about what we're calling things. If I say like, let's say that X is, oh, what do I want to call that? Is the age of an unemployed resident. So I could ask something like, what's the probability that X is between 15 and 35? Well, what's the percentage or fraction of people that are unemployed between 15 and 35? Well, between 15 and 35, there's 4,000 out of 7,000 people. So that's going to be 4,000 out of 7,000, or 4/7. Wow, that's not a 4 on top.
So I have a question. Is relative frequency the same thing as like percentage that they're asking for?
Totally. I'm just writing. Well, it's not percentage. It's the decimal equivalent, right? So if I like, for example, if I simplify this, this is approximately equal to 0.1428. So I could say that what percentage. So if I asked this another question like, what's the probability that the age of someone unemployed, so X, in this population is between 46 and 55? Oh, I should have said, I feel like I made a, whatever, it's fine. I would say that the probability there, depending on the way you want to write the answer, well, it's 1/7, which you could say is 0.14 approximately, or 14%. Right? You can answer it either way. And it really kind of depends on how they say they want the answer to look. So that's kind of the idea here, is that if you're being asked to find a probability of something happening in a population, you're just being asked to figure out, well, how many people or how many observations have that thing you're asking about. So, okay, he's talking about all sorts of things like this, sure. An example people also like to use is rolling a die. I forget if die has an E or not, to be honest, but whatever. Or rolling 2 6-sided dice. So sometimes people ask questions like, what's the probability that the sum of the 2 dice is, say, equal to, I don't know, let's say 4. Well, to know the answer, or to find the answer, there's a couple things you have to know or figure out. You have to know how many possibilities there are in general. So the total number of possibilities is actually kind of large. There are 36 different things that can happen because each die has 6 possibilities. So you can make a big old table. It's kind of a pain to make. You can say, like, here's die 1, here's die 2. You can say the possibilities are 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. When I find myself having to think about 2 dice or 2 of the same sort of thing, I think of them being different colors. Like 1 die is red and 1 die is green. So this is the green one up here. I could actually use colors. I'm not going to because we're almost out of time. So I could get a 1 and a 1, or a 1 and a 2, or a 1 and a 3, or a 1 and a 4, etc. I can get a 2 and a 1, or a 2 and a 2, or a 2 and a 3. I can get a 3 and a 1, or a 3 and a 2. I'm not going to complete this because I know we're almost out of time. Again, make sure you fill out the attendance sheet. Again, I will throw that link on there one more time on the chat. So please do fill out the attendance. What I want to say here is that here we have a total of 36 different things that can happen. The red die can be 1, the green die can be 1, or the red die can be 1, the green die can be 2, so on and so on, all the way up to 6 and 6. Out of those 36 total possibilities, which I believe is called the event space, there are exactly 3 ways of getting what we're asking for. You could have the red die be 1 and the green die be 3. You could have the red die be 2 and the green die be 2. Or you could have the red die be 3 and the green die be 1. So there are 3 ways to roll a total of 4 out of 36 total possible things that can happen. So the probability that the sum of the, you know what we call the little dots on the die? We call them pips. The sum of the pips is equal to 4. The probability that happens is, well, there's 3 ways to get that out of 36 ways total. So that, and then you can reduce that fraction. I don't really care, right? It's 1/12. That's kind of the idea there. So I know we're out of time. Again, I will say for class next Tuesday, definitely come with questions. I imagine you guys will see a lot of material on Friday and on Monday before we have class again. Also, I will post a quiz. I'll try and post it sometime sooner than Monday, like maybe Saturday or maybe Friday even. And again, do the quiz, you get full credit. It's just an opportunity for me to give you some feedback on material. So go ahead and I will definitely, once that's up, I will let you know and you guys can do it. If you have a question you want me to answer, you can always start a discussion on Canvas and I will answer it, or one of your fellow students can comment. But again, participation is great. The more you guys ask for, the more I can help you out. All right, I'll let you go. I'll post this video up on YouTube shortly, and I will see you all on Tuesday. Bye.